All right, we made it to isotopes and atomic mass 2.3, and I included 2.4 in this video because they go together, and we're going to talk about isotopes and atomic mass and then radioactive elements and the effects of those on health, on biological beings. So we know that atoms of the same element have the same number of protons. So if we see 6 protons, we know that that is carbon. Those are carbon atoms. Okay. But we can have different numbers of neutrons. Okay. So not all atoms of the same element have the same mass, right? Because the neutrons are added to the protons, and that's how you're going to get the mass, right? So if you have different number of neutrons, then the mass number changes. All right, so if you have atoms of the same element, but they have different mass numbers, those are called isotopes. Okay, so we called those mass numbers in the last class period to kind of keep it simple, but now we're going to go into a little more detail about that number. So an isotope, you have an atom of the element carbon. Okay, so if you're going to write that in notation, symbolic notation, you can have your carbon, and let's say you have 12 and you have 6 here. So this is your protons, and here you have your protons. Oops. You're going to have protons plus your neutrons. All right. So that here we have carbon, okay, and in here we have another carbon. Let's say that the mass number, the total mass is 13. And the protons, though, that's still going to stay the same. Remember, it's always going to be 6. Okay, so 6 plus what is 13? 7. So the neutrons have changed. Here, in the first one, if you have, let me write it again, if you have this carbon, or you can call that carbon 12, as you see right here, carbon 12, you have 6 protons and you have 6. So you know that means you have 6 neutrons because this is protons plus neutrons. All right. Carbon 13, carbon 14, the protons stay the same, but the mass number is changing. Why? Because the number of neutrons changes. So here you have 7 neutrons. Here you have 8 neutrons, so on and so forth. So these are isotopes. They have the same number of protons, but a different number of neutrons. All right. And I showed you the symbolic notation, and also that you can call that carbon 12, carbon 13, carbon 14. And we'll use carbon as an example a lot. So the number below each of those elements on the table shows the average atomic mass. Okay. So you know that that mass number can change now. So what you see on the table is you see that decimal. That is the average atomic mass, because you notice it doesn't just say 12. So I'm going to show you what that means. The average atomic mass depends on several different isotopes. It's the average of the masses of all of those isotopes, but it's not just an average, it's a weighted average. All right, I'll show you what I mean. So most of the carbon that you might have in a sample is going to be carbon 12. Okay, so that's what's going to be represented in this average atomic mass. Okay, so it's proportionate to each of the isotopes in a sample. All right, so in your sample, most of that carbon, it's probably going to be carbon 12. So that's going to be the most weight. All right, so, and then next, you might have carbon 13. All right, and then even less than that, you'll have carbon 14. So if you were to just do a regular average, then you would have 12 plus 13 plus 14 equals 39. And then you average that. So you divide by 3, you would get 13. So then it would look like, as an indicator in this table, if this number said 13, then it would seem like most of the carbon that you find is, is carbon 13, but that's not true. So instead it's a weighted average. So you're going to get, so let's say carbon 12, 99%. So move your decimal. So you're going to multiply by 0.99. Okay. And here you have 13. Let's see. All right. Move the decimal. So 13 times 0.01. And you'd have carbon 14 multiplied by 0.0001, something small like that. And so then you average that together, divide that by 3. And that is how we actually work this out to get 12.01. All right. So when you have an atom that is giving off radiation, or giving off energy, rather, an atom that is spontaneously giving off energy, this is called nuclear radiation. Okay, so elements that emit radiation are called radioactive. Okay, that would be a radioactive element. All right, so this occurs in unstable atoms. You find this in nature. You find this in human-made sources. So you can find this in a lab, or can be made in a lab. So this originally happened, or was originally discovered in 1896. Henry Becquerel and 2 other scientists were collaborating with him, Marie Curie and her husband Pierre Curie. The Curies, they got an exposure on a photographic plate, which, with it like a film, normally you'd have to expose to light, but they just placed this plate in the dark with uranium, and they developed a photograph. And so they knew that there was something about this material. All right, something was emitting something. It was radioactive, right? So most naturally occurring isotopes are not radioactive. Okay, some are, but most naturally occurring isotopes are not radioactive. They're stable. All right. Whenever they are not stable, they start to become stable by emitting radiation from their nuclei. All right, so that is called radioactive decay. All right. All right. So some are naturally occurring radioisotopes. All right. So radioisotope. All right. So look at these words. Radioisotope. All right. There are isotopes that emit radiation. All right. So they can be mined from the earth, naturally occurring, or they can be made in labs. All right. Mostly they are prepared in labs, and they are used to serve our purposes. All right. So all of the isotopes with an atomic number that's higher than 83, those are radioactive. But there are some exceptions, like gallium. So if you have gallium, right, so you have a stable gallium, so 69 and 31. All right, here we have this stable atom setup. If you then have gallium that is 67, and so you take 2 of these neutrons, you take 2 neutrons, you have unstable gallium, all right? It's not stable, all right? So you just changed the mass number because you took 2 neutrons. The number of protons stays the same, right? So this is radioactive. All right. And so actually, this is a radioisotope used in cancer treatment, or diagnosis rather. Cancer diagnosis, excuse me. Diagnosis. So we're going to talk about 3 forms of radiation. That would be alpha, beta, and gamma radiation. All right. And there are positrons and neutrons. So we'll come back to this slide as sort of like a review after we go through the definitions of each one of these types of radiation. Okay, so let's start with the alpha particle. That's represented by the Greek letter alpha, or the helium nucleus containing 2 protons and 2 neutrons. See, because that's our proton, and here we have our proton plus our neutron, okay? And so when we have this helium, like without electrons, oh, it has this positive charge. So this is the alpha particle, all right? And furthermore, next, we're going to talk about the beta particle. So that's represented by the Greek letter beta, or symbolically as like E, like electron, right? So this is a very high energy particle, and it carries a negative charge of 1, all right? And this is because you have a neutron that ejects a beta particle, and then you end up having a neutron that becomes a proton as a result. So that neutron is ejecting a beta particle, so that's something negative. So then it becomes a proton, think positivity as a result, okay? So this is a high energy particle, high energy, all right? And it's going to be somewhat comparable to a positron, and we'll get to that. Okay, gamma rays. So more high energy radiation, okay, that's emitted during radioactive decay. So that's whenever you have the unstable becoming stable, right? So those aren't particles. So whenever the gamma rays are released from an unstable nucleus to a more stable state, they are releasing rays, all right? And so the gamma ray is represented by gamma. And here we have no mass. No mass. And so you see that represented this way. Okay, so we have here, because we have no mass, what does that mean? That's no protons, no neutrons. No protons, no neutrons. All right. So basically, gamma rays and X-rays are kind of similar, but gamma rays are way more potent. All right, I think you'll see that in your problems. So moving on to a positron, so kind of comparable to the beta particle, except it's positively charged. So it has also the same high energy. So it's high energy, the same mass as that high energy particle, has the same mass as the high energy. Same mass as the high energy particle. That's the beta one, right? So it looks very similar. Okay, so the decay changes the proton to a neutron and emits a positron. And then the positron collides with an electron, and that will emit gamma rays. Okay, so basically, this is something, if you want to know the application, that's used in PET scans. Heard of a PET scan? All right. So We're almost there. Bear with it. A neutron has no charge, okay, no charge. And it's represented in, like neutron, all right, you have 1, okay? So they can be used to cause radioactive decay. So neutrons can be used to cause the radioactive decay, all right? So as an example, if you have this boron, and then you have this neutron come by, all right, and it's bombarded into this boron, then you can get this unstable boron, all right, see? The neutron numbers went up, so that mass number went up, all right? So this is unstable. And that then undergoes radioactive decay and causes radiation, all right? So we talked about our positively charged particle, alpha. All right, you see here that that was a positive 2 because we don't have the electrons. So then you have a surplus of 2. Okay, that's what's happening with alpha. You have our negatively charged particle. All right, the beta. We have our gamma, which is neutral, our positron, which is positive, our neutron, which is 0. And so you remember this is like helium, no electron. Okay, the beta, we have our high energy. And gamma, we have our no mass. Our positron, we have our proton that goes to a neutron, emits a positron. And neutron, where we can achieve an isotope undergoing radioactive, that will undergo radioactive decay, right? Take some time, become a little bit familiar with this jargon. All right, so I know a lot of people are biology majors in here, so this might be where it starts to get a little more interesting for you. So we're talking about the biological effects of radiation. Okay, so radioactive emissions, they have a lot of energy. They're going to interact with anything, okay? Whether or not it's in a living organism, but definitely with living organisms. That's why it can be dangerous, very dangerous. And you have to take a lot of precaution when you're working with radioisotopes or radioactive isotopes. So you'll have alpha and beta particles, your neutrons, positrons, gamma rays, and X-rays. They are all, so they are ionizing radiation, okay? They are ionizing radiation. So, so that means ejecting an atom's electrons, and that is dangerous. That makes an atom more reactive, very unstable, okay? So the loss of electrons in cells, they affect everything about a cell. The DNA, all right, the genetic material can cause adduct formation, can end up causing cancer, all right, with a certain amount of radiation. So, you know, this is why we have to avoid these types of radiation. This is why we don't keep uranium or radium in our pocket. Okay, so the radiation of a higher energy penetrates farther into the tissue, affecting those cells that are deeper in the body. Okay, so you have to keep that in mind whenever you're working with different forms of radiation. You should have certain levels of protection. You should have, if you should be working under a hood, where you should have a few shields between you and that material, a lab coat, glasses, gloves, and you may stand behind a plastic or a lead shield or a glass shield of some sort. So one thing that you have to do is wear a badge. And so wherever you're working at this lab, the safety, what do you call those people? They're not safety instructors, but they're in charge of safety. They will require you to wear a film badge to monitor your total exposure. So it records how much radiation you're exposed to. You wear it on your lab coat, and that gives a certain number to the people who routinely work with radioactive materials. And if that number gets too high, you can never work with radioactive materials ever again, because you're going to cause yourself to have cancer and even radioactive contamination, which is much easier than you may think. So you're going to use different degrees of protection depending on the type of radiation, the type of radioactive material that you're dealing with. If you are looking at something with an alpha particle, all right, usually your skin is going to protect you there. Okay, if that becomes aerosolized and you inhale that, your lungs are going to be exposed, and then you could have more internal damage. All right, some of your mucosal membranes and your internal organs can be at risk, but most of the time you're protected with your skin, and so on and so forth. With beta, you need even more protection, and with gamma and x-rays, you'll need some form of lead protection, and with neutrons, you need the most protection, concrete. All right. And so here is a summary of all of the particles that we talked about in rays. So it shows you the travel distance through the air, tissue penetration, right? How deep does it go into the body? The deeper it goes, the more damage, okay? So how much is too much? All right, how much radiation? How much causes a problem? How much causes a problem? Well, so the biological damage is measured in sieverts. All right, that's the SI unit. But the amount of radiation is measured in millirems, all right, equal to 1/1000 sieverts. All right, so we're always exposed from cosmic rays, all the stars out there, to ionizing radiation, but it's not a whole lot. A lot of it depends how much for how long. And it's really been a lot since the 1980s. We're up 40%. That's because of what we use radiation for, to diagnose and treat diseases. So it's mainly that. So we're, in general, we are being exposed to more and more radiation. Okay, so when you're exposed to a certain amount of radioactivity, you can have radiation sickness. All right, so what I mean by that, and that depends on both the time and the dose, and there's going to be a chart on the next slide for that. But it depends on if it's long-term for low levels, you know, you'll probably be okay. But if you have a short, intense dose of radiation, you can get severely sick and not be able to recover. You can have a lot of side effects. It can be fatal. And yeah, if it's fatal, obviously you're not going to recover from that. And so your cell types that are rapidly dividing, like white blood cells, cancer cells, okay, those are killed off more quickly than others. So we use it as a treatment for cancer. So the radiation will kill off those cells more quickly, but there's going to be off-target effects like your white blood cells. So when you have these cancer treatments, that's why it brings down your immunity, your white blood cells are what protects your body from infection. Your hair cells are rapidly dividing. So it's also that can cause hair loss when you have treatment with chemotherapy. Or you have your stomach lining that produces mucus. So you can have problems with those cells that produce mucus that protect you from the acid in your stomach, and you can end up being nauseated and throwing up. So those are some of the side effects from cancer treatments, being radiation. And so you can see in the millirems, like 5,000 to 20,000, the clinical effect is not detected. It's not so much. 20,000 to 50,000, even more, you see some decrease in your white blood cells. All right, when we get up to 100,000 to 200,000, this is poisoning. This is radiation poisoning. And that's where you have loss of appetite, nausea, and hair loss. When you get to this point, moderate radiation poisoning, you can have permanent damage, okay? And you know, it's going to take you probably a long time to recover from that treatment. And the lethal dose for half the population at 30 days, 300,000 to 400,000 millirems. That's a lot. And so that table is a pretty good summary. All right, I'm going to stop there, and we're going to go through some problems for 2.3 and 2.4. All right. So here we go, 2.3. So now we have to sort of change gears and go back to our 2.3 isotopes and atomic mass thought. All right, but the mass of the isotope carbon-12 is exactly 12 AMUs, atomic mass units, all right? The atomic mass for carbon, as seen on the table, is 12.01 AMUs. Explain this difference. I think that we are going to go through these problems. Let's save these ones for class. Let's do these. Let's do these right now. Okay, we're going to do this activity. Discovering the concepts. Inquiry activity on isotopes. All right, so now you see, and we're not saying, you know that this is the electron clouds. I don't have to announce that anymore, but you have 20 electrons here and 20 electrons here. Okay, you see that? These are isotopes of calcium. So you have 20 electrons there, which means you have 20 protons here, right? You know, those proton and electron numbers are staying close. And what you have that is different is what? This number right here, the mass number. All right, so you have calcium 40 and you have calcium 42. So these are isotopes of calcium, right? Because they must have a different number of neutrons. Here you have 2 more neutrons. 2 more neutrons. All right. You have 22 neutrons, 20 protons. All right. So the questions, how many protons are found in calcium 40 and calcium 42? Well, if it's calcium, it's always going to be the same, because if it's an atom of calcium, those protons aren't changing, right? So what's your answer going to be there? Right? It's 20. It's got to be 20 because it's calcium. Okay? You're always going to have that number of protons. That's what makes it calcium, gives it its properties. So how many neutrons, make this a little bigger for y'all. Whoop. How many neutrons are found in calcium 40 and calcium 42? Okay, so we just went over that. How many neutrons in calcium 40? Well, you have 20. So you have 20 protons plus 20 neutrons. So you have 40. Here you have 22 neutrons plus 20 protons, and that's what's giving you 42. So for 40, you have 20 for calcium 40. And for calcium 42, you have 22 neutrons. All right. What is the relationship between the number of protons and the number of electrons in an atom? Okay, so what is the relationship between the number of protons and the electrons? We went over that already. So the relationship is that they are what? 20, 20, 20, 20. They are equal. All right. They are equal. Based on the information, what is common to all calcium atoms? What is common? We just talked about it. What's going to stay the same? The protons, so therefore electrons, all right? P and E. Okay, what could the atomic number Z indicate? So we're looking right here, the atomic number Z. What does the atomic number indicate? The number of protons. So we're basically just using repetition. We're saying this in a bunch of different ways, and that's going to help you to understand or to remember. How is the mass number A found? Right? Do you remember how mass number is found? That would be protons plus the number of protons plus the number of neutrons. All right. So from the information given, how would you define an isotope? How would you define that? So they're atoms of an element, right? So that would be like carbon 12, carbon 13. So they're the atoms of the same element, which means they have the same number of protons, same number of electrons, but different neutrons. All right, that's isotope. So give you a little review from before, and now we're adding something new. Where are the protons, neutrons, and electrons located in an atom? The protons and neutrons are in the nucleus. The electrons are in the electron cloud. Okay, so what do all calcium isotopes have in common? How do they differ? All right, let's see. What is common with the isotopes? How do they differ? So what's common would be, I feel like we already answered this. They have the same number of protons, the same number, so they have the same number of protons, the same number of electrons, and they have different number of N. All right. Neutrons. So where is most of the mass of an atom? All right. That is in the nucleus, right? Because you have protons and neutrons there, and they both are larger than electrons. Right? Electrons are 2,000 times smaller. Okay, so this is all for that section. We're going to do 2.3 in class. So I think there's not that many of those. All right. And so we're going to do a few problems in 2.4. Okay, so 2.21. If the symbol for an alpha particle is this, explain how an alpha particle differs from a helium atom. Okay, so what is different? Well, the alpha particle has +2 charge, so the difference is no electrons to balance out that charge and make it neutral, like helium, all right? Okay, so 2.23, which form of ionizing radiation has the greatest penetrating power? And you can go back on your slides, but the greatest are those gamma, and remember the one that you need concrete? Your neutron. All right. So 2.5, how much radiation is the average person exposed to annually from all sources? Okay, let's see. Well, we're going to skip over that one, I think, and we're going to do 2.6. All right, so let's actually, no, we're going to do it. We're going to do 2.25. How much radiation is the average person exposed to annually from all sources? All right, well, so we can look at millirems and we can look at sieverts. So for sieverts, that will be 0.062. And from millirems, you can say that that's 620 millirems. All right. That's silly. What am I doing? 620 millirems. All right. So that is the amount of radiation, all right, per kilogram. All right. This is the clinical damage, biological damage. All right. Here you go. How do you feel about going to the dentist? Your allied health applicable question. A routine dental exam often includes 4 bite wing x-rays exposing a patient to a total of 5 millirems of radiation. Would this cause radiation sickness in the patient? If so, what would be the effects? Okay, well, so the max amount of radiation without clinical effects is going to be 20,000 millirems. Okay, so if you have only 5 millirems, then you would have to divide this. So if you divide this number by 5, that means you would have to get 4,000 sets of these x-rays to have those effects. So yep, definitely go and get your routine dental exam done. It's probably better that you do. All right, so I think we're going to solve these other problems in class, and that's it for this video. Thank y'all.